We can also conduct hypothesis testing for the correlation coefficient. Okay? Again, this is the case in which you have a random sample from a population and you want to say something about a correlation in a population. Right? These steps should by now be quite familiar with you. When we conduct a hypothesis test for the correlation coefficient, we're going to use a test statistic, a t-test statistic, but we're going to use statistical software for the computation and interpretation of hypothesis testing for the correlation coefficient. You do not need to do anything by hand. The math is a little bit more complicated. What's important is that you understand substantively what's going on and how to interpret the results. So we're going to use statistical software. Here's the correlation t-test. Right? We get a p-value. It's less than alpha of 0.05, so we're going to reject the null. You can see the statistical software output also gives us a 95% confidence interval for the correlation coefficient. So we can say we are 95% confident that the true correlation of the population is between 0.144 and 0.658. Again, we're doing this because if we had the population, we could just look at the correlation. Say, oh, that's the correlation of the population. But since we have a random sample from a population, we want to make an inference. We want to use this random sample to say something about a correlation in a population. We can also conduct hypothesis tests for regression coefficients. Right? The regression coefficients in simple linear regression consist of the intercept and the slope. The tests and the steps, quite similar. Right? For the regression coefficients, they are based on the t-test statistic. Again, similar to the correlation coefficient in terms of inferences, we're going to use statistical software. You won't have to calculate the actual underlying test statistics for regression coefficients by hand. We want you to substantively understand what's going on, however. The t-test statistic for regression coefficients is commonly called the t-ratio. Sometimes it's called the t-value. Right? The form is as follows. Okay? It's basically just the coefficient minus 0 divided by the standard error of that coefficient, or just that estimate divided by its appropriate standard error. Right? This test statistic, this t-ratio, it lies on a t-distribution with a certain degrees of freedom, and it's interpreted as before with other test statistics. It tells us how far a sample coefficient is from the null hypothesis, right? Assuming that the coefficient in the population equals 0. Right? Again, we're going to use statistical software to obtain the actual standard error for the t-ratio. Here's an example of output from simple linear regression. Okay? This is using the cricket chirps data. All right, we can see that the t-ratio, the t-value is 16 roughly for chirps. It's statistically significant. You can see that t-value is 16, and if you know anything about the t-distribution model, that's pretty high. Okay, you can just look at the t-ratio and say, well, that's quite a bit above 2. Right? As a rule of thumb, that's statistically significant at the alpha 0.05 level. In fact, the annotated output, those 3 asterisks, tells us that this is statistically significant at the alpha 0.01 level, the 0.001 level rather. And so it tells us it's very unlikely to obtain this coefficient under the assumption that that coefficient is 0 in the population. Same with the intercept. It's very unlikely to have obtained this coefficient if in the population the coefficient is 0. Again, we're doing this because we have a random sample from a population and we want to say something about this regression model, these coefficients in the population. If we had the population, we could just fit the regression model of the population and we wouldn't need to conduct these statistical inferences. After you conduct regression analysis, it's also useful to consider basic regression diagnostics. Okay? There are a few diagnostics. These are assumptions of regression, and we can use information from the sample to kind of test the validity of these assumptions. One assumption is that the relationship between our x variable and our outcome is linear in the population. We can check that by looking at a scatter plot between x and y. Are these two variables linear or not? If they're not, we might question that assumption about the population. Number 2, we assume that the standard deviation of the outcome is the same for all values of the x variable in the population. So what we can do is we can check a scatter plot between the residuals, the errors, and x. Right? We want it to look kind of like noise, approximately. Right? We don't want to see a fanning effect or anything like that. Third assumption is that the outcome variable is normally distributed around the population regression line. So we can again check a histogram of the residuals overlaid with a normal distribution model. Right? We want the idea is that these, even though these are in the population, these are assumptions about the population. Right? We can use a sample of data to kind of check the validity. Right? The idea being that if there's some kind of discrepancy, we might question or might think about how to refit our model through transforming the data. And that's how we deal with possible violations. If you think these assumptions might be violated based on diagnostic plots, you can apply nonlinear transformations, such as logging a variable that can reduce skew, that can make a variable or a relationship between two variables more linear. It's kind of like straightening out a coat hanger. You can also remove outliers. So previously we removed an outlier of Haiti when we were looking at life expectancy and population growth. So you can remove an outlier to improve the model fit, which might help you deal with possible violations of these assumptions. Again, these are assumptions in the population, so we can never be entirely sure until we have the population. But the idea is regression diagnostics are always useful to consider possible issues. And the idea really is to make sure that we're not deceiving ourselves when we fit a regression model to a set of data. And with that, we really cover the main parts of this course. There are additional aspects and issues you should consider when studying for the final exam. But in general, these are the main points that you should get away with. Now, one sort of final point I should say is that, just as a final note, there's a huge demand for statistics right now. That's because there's a huge growth and exponential growth in the availability of all sorts of data from the internet. So you have satellites, you have cell phones, you have surveys online. We have so much data right now, we don't have enough people to analyze all of these data. In addition, it's not just enough to to analyze these data. We really need people to tell stories or give meaning to these data. This is why statistics is not equivalent to math. Data visualization is a very big field. In addition, we need people to help us interpret what statistical analyses are telling us. So that's why you can't always be a specialist in a particular field. Sometimes you need to understand substantively what's going on. So sometimes if you're interested in anthropology, sometimes an anthropologist doing statistics, because of his or her substantive background, can better interpret numbers and counts and statistical models. So there's really a big demand for people to tell stories and give meaning to data, and also to learn how to analyze these data. So the bottom line is that there's a huge demand, and we have far more data than people to analyze these data. That's why if you look at the job outlook, according to the Bureau of Labor Statistics through the US government, you can see statistics and statisticians and data science. That's really the job of the coming decades, right? That's what they point out. And so you can see that learning the material of this course, I think, will really help you progress in the future. And here's just a smattering of headlines over the past couple of years. You can see for today's graduate, just one word, statistics, or today's sexy job, statistician. Data scientist, the sexiest job of the 21st century. The point is that the material you learn in this course is statistics, data science, a little bit of programming, a little bit of data visualization, some graphic design. But the idea I want you to take away from this course is that going forward, we want this material in this course to leave this course. We want you to use this material in your own field of expertise and really use the full power of statistics in your life and to help us understand the world around us.